Okay, I'll go ahead and start my presentation here. And sorry for the brief intermission there. So as Paul mentioned, I'm Jim Cale, and I manage a group at the National Renewable Energy Laboratory. We're in Golden, Colorado. And today, what I'm going to talk about is really ties to what Paul said earlier, which is a lot of the systems and components like PV systems, wind energy systems, they already exist. They've been vetted in a variety of applications. And what's really needed is to go beyond just the component level and really look at systems level implementation. So I work under a newly formed directorate called Energy Systems Integration at NREL. And I'll be talking about what ESI is and the importance of ESI in a moment. But I'll just tell you up front before I start my presentation that the thinking within government, and in particular DOE and the national labs, is that our current energy system needs a dramatic redesign. At the very least, it needs to be reconfigured with new technologies overlaid on the existing infrastructure. So I'll talk about that in detail during my presentation, the title of which is Designing the Future Energy System for Cleaner Air, a National Laboratory Perspective. And I think it's worthwhile just to mention at the outset just the relationship between the national labs and DOE, if you're not familiar. But you probably know that DOE is a cabinet-level department within the United States government, and its purpose is to really advise the president directly on policies regarding energy. And as you know, energy is highly interrelated with and influences our economic prosperity. So the current Secretary of Energy, Dr. Ernie Moniz, is pictured here. And I have highlighted also that DOE sponsors more research in the physical sciences, that's including electricity, delivery, and reliability, for instance, than any other U.S. federal agency, the majority of which is conducted through its systems of national labs. So they're also called FFRDCs, or federally funded research and development centers. And NREL in particular, where I work, it's the only national lab whose sole mission is to advance renewable energy technologies. It started in the 1970s under Jimmy Carter as a solar energy research institute, and the goal then was to increase the efficiency of PV. If you remember back then, PV, as Paul mentioned, was just a dream. And now it's to the point where it's being mass produced in the US and elsewhere. It's become a lot cheaper and more viable. So now if you look at the main campus of NREL, we've expanded much, far beyond just solar. And I have a few laboratories mentioned, but thermal test facility, field test laboratory building, distributed energy research, and several others. And I'll actually be going into detail on a building right back here on the top of this figure. This is the Energy Systems Integration Facility. So going back to what Paul said, trying to solve the research problem of integrating systems together from both a interconnection and controls and communications perspective. So here's a picture of today's electricity grid, and not to bore the utility people in the room, but the way that the model here has been the same for the past 100 years, in the sense that you have large generation. So I have nuclear, coal, hydro, and others. That power is typically boosted up to transmission levels. It's transmitted down to distribution, and then to the residential or commercial entities. By the way, that transmission of energy from the generation to the customer results in an energy loss. There are various estimates, but 5 to 7% loss right there. And that's primarily because generation and load are separate. And another thing that you'll notice, if you look at these red arrows here, primarily, historically, that load has been serving customers that are passive loads. So the two components of that, first of all, passive, meaning that customers historically haven't had the ability to really control their load. And whenever they do have a demand, they flip on the switch or the air conditioner comes on, they pay whatever the utility says the price is. And on the same side, on the demand side, it's load. So primarily, historically, the customers have been load to the utility, not generation. Well, as you probably know, that picture is changing very rapidly. And this is a picture of the emerging integrated grid. So two things that I want to point out. First of all, large-scale wind systems, large-scale solar systems. These are connected here, showing a connection and a transmission. but also on the distribution side. So if you see this home, this is what we smart home, but composed of various components: energy storage, electric vehicles, and others. So I want to point out a few things here. First of all, in terms of solar energy, I mentioned that the cost has come way down, the viability has come way up. I think that it's sort of a watershed in my mind when you look at someone, a conservative value investor like Warren Buffett, actually investing in solar power plants. So that shows you that there's a return on investment of solar in large scales like this in certain areas of the country. Well, then if you look at down at the distribution side at the home level, what we're now seeing, I guess maybe 2 or 3 years ago, utilities started hearing the word about, for instance, microgrids, so islanded systems, people that wanted to disconnect from the grid. And we started getting calls from utilities that were strategic business units inside utilities asking, is this a real threat to our business model? And then you really couldn't point at very many applications where people had islanded from the grid. There are a few universities, a few military bases. Well, now I went to a conference 6 months ago, and you wouldn't believe the number of vendors who are starting to look at microgrids as a real possibility in developing products and control systems. So as a national laboratory, we do fundamental research. We can influence policy through that data, but really the markets drive which direction that our future energy system will go. So we don't know if every home in the future, for instance, will be microgridded. I think there'll probably be a hybrid solution, that the utilities will still exist, but there will be the ability to disconnect from the grid. And the question is, how will utilities respond to that? Will they, for instance, some utilities are looking at, can they get in the business of operating equipment, operating microgrids? Again, there's a lot of policy implications, and when you get into the changes in utility business models, it's a complicated discussion. Nevertheless, these are some of the changes that are happening right now, and as Paul mentioned, very rapidly. And what's needed now is the ability to integrate these systems together. So for instance, if you were to take a home such as this, could you connect multiple homes together in neighborhoods, or could you even expand that to a regional area? And the drivers here behind this, commercial and social drivers, are, first of all, if you would ask yourself, is this really going to happen? First of all, the information age, there's a lot of talk about the Internet of Everything and ubiquitous sensing and the ability to get data from many devices. And I can tell you, I'm a late Gen Xer, and people that are my age or younger have a voracious appetite for data, and they want to make decisions on that data. And as a matter of fact, 5 years ago, I think, I couldn't have walked down the streets of Dallas, looked up a barbecue restaurant, looked at the Yelp reviews, and actually make a decision in terms of which door I'm going to enter based on data. And once I have that data, once you have the ability to make decisions on that data, people not only they need it, they not only have a desire for it, actually it's part of their lives. So it's a natural progress of energy, of industry, and theoretically it would enable better asset control and management. But it requires a few things. First of all, advancement in highly distributed controls. So that means the ability to have a large number of generation assets at the home level, for instance, energy storage, and other types of load, controllable load, and the ability to manage all those assets and to be able to connect and disconnect from the utility at will. In addition, cybersecurity. It used to be, several years ago, I thought that people that were afraid that, the government was going to look into their smart meters, I thought this was, for the most part, unjustified. However, around a year ago, I heard a presentation from a woman she was a single woman, and she said that, well, if someone would hack into my smart meter and they found out my usage of energy, they would know when I'm home, so it's a security issue. And I thought, well, that's a good argument. That makes sense. But even more so, in terms of cybersecurity, once you get more technology embedded in the grid and the ability to segment the grid in order to make it more resilient to disturbances, then every component of technology that you add, obviously, cybersecurity becomes more of an issue. And if you would look at, there was a quadrennial energy review that was initiated by Obama back in January. And one of the outcomes of that, I heard a presentation on it, one of the outcomes was that maybe 63% of the cyber attacks in this country over a rolling one-year period starting in 2012 about 63% were on critical infrastructure, like electricity, and those are interconnected with fuel systems. So it's very important that as we build out the energy system, the future energy system, that cybersecurity is a primary component of that, and I'll show you a little bit later how DOE is addressing that. Also need to integrate large amounts of renewable energy. So it's mentioned in terms of PV and wind that those are spatially distributed, even down to the distribution level. And they're variable and uncertain, meaning that they're variable because, for instance, the resource changes during the day through cloud cover, for instance, and uncertain, meaning even when it's daytime, there may be clouds, the uncertainty in terms of or variability in terms of PV operating in the daytime and wind at night. So because of those two aspects, they require additional controls. And also sustainability as a political and social value. So we have the national goals to reduce greenhouse gas emissions in addition to the traditional economic and reliability metrics. The reliability, or the grid has to operate as economic and reliable as it is now. So you have these additional technologies, but still the same constraints. And one other thing I'll mention is, we're moving towards a point now where energy can be seen as much more than just a commodity. So a commodity, by definition, regardless of where you get it, you don't pay more for it. However, there are some counterexamples that I think are relevant to me, my generation. And that is, for instance, my wife will pay three times more for a salad if she knows where it came from, if it's organic, et cetera, from Whole Foods, versus another grocery store. So, but isn't food a commodity? So it's true that if people know it's a social value and people know the source of the energy, they'll actually pay more for it. So that can change the dynamics, market dynamics as well. So what I want to talk about now is, in order to address the problem of energy systems integration, what our strategy is here at NREL. And there are two components, and the first one is just going beyond electricity. So if you look at electricity as just an energy carrier, in addition to thermal systems, fuel systems, then we have to look at synergies among these systems. So Paul mentioned the thermal, tie into the thermal loops to get a LEED Platinum certification. So there are lots of opportunities in the grid that, for instance, you can use the thermal mass of a building for temporary energy storage, as I'm sure you're aware. But the other component, I think this is the most important slide that I have today, is a layered architecture for the future energy system. So the way that we envision the future energy system is composed of these 5 layers. It's the LASIK, or the Layered Energy Systems Integration Capability. The way it works is, fundamentally, to date, a lot of government research, or academic research, and others in industry have really been at the component level. So if you look at this bottom layer, the device layer, I mentioned SERI and the advancements in efficiency with PV, wind generation, and others at the device layer. So these are the actuators, as it were. Above that, so each of those devices typically have a local controller, so an embedded controller, microcontroller, using TI chips primarily, probably. And then that has to be optimized at a system, what we're calling the system control layer here, through a cyber and information layer. And that system control layer really forms an optimization, solves a complex optimization problem, which has inputs from policy, economic functions, business models, and markets. So we envision a time in the future where there's a real-time price, or a real-time market for electrons, as it were. So you have a futures market for gold and silver. If your controllers at the home level, or those aggregators of those control systems in the home, could tap into a real-time energy market, then they can perform optimization functions, arbitrage, for instance, in that market. So we have to prepare for a world where that is accessible. So you might look at this and say, well, if the entire energy system were composed of these devices, and they're all being optimized at the system control layer, how could you solve? That's a intractable computational problem, and that's true. So what's needed here is really an architecture such as this that's scalable, meaning that this architecture should be able to be used at the home level, but it should be able to seamlessly connect to other homes in a neighborhood or even a region. And that's through the use of what's called multi-agent control, meaning that I have an agent, as it were, that looks out for the needs of an individual home and can broker deals with other agents inside the energy system. So this is some of the architectures that we're looking at. So you might look at this and say, well, this is sort of similar to another problem that we solved several decades ago, which is basically, DARPA funded a project that said, well, inside the government computer network, if one computer goes down, I don't want the whole network to go down. So that instituted the creation of the internet through, and the reason, or the way that was done was through standard semantics through the TCP/IP protocol. So what we need now is a standard semantics and protocol for the energy system so that it's scalable. So that's just one idea that research is ongoing at NREL. And I was also asked to talk a little bit about energy efficiency. So another provocative idea, and I'm sure this was discussed, is if you look at commercial building loads right now. So I got this chart from a commercial buildings researcher who told me that about 50% of the load, including lighting and what MELs, the miscellaneous electrical loads, form about, conservatively, 50% of the energy in a building. And he said that, and even in the heating side, usually they don't care if it's AC or DC. So the question is, why are we still distributing power inside buildings using AC? So going back 100 years, it made sense because when you're transmitting power, AC is better. But if the generation is in the building and it's already DC and all of your loads are DC, like plug loads, then why are we doing that? Why are we converting between AC and DC? So to maximize energy efficiency, why not serve DC loads and sources with DC distribution? So this is an idea that's being researched at NREL and other labs. And moreover, I'll show you some research test beds that we're using to investigate these concepts. So I wanted to just talk about, what are the different investments by DOE and from the national labs to look at energy systems integration. And about 2 years ago, we constructed this building. It was a $130 million investment by DOE to do energy systems integration. So before I showed an overview of NREL with the various laboratories, so if you take those labs and those program areas and put them all together in the same building and force them to work together, that's what ESIF is. So starting over here to the right, this building here, sort of a tan color, that's a distribution transmission, a smart building group, and a resource assessment group. This is where my group sits, about 200 researchers. And then a little bit, down the corridor from that, there's a high-performance computer and data center. It's a 1.2 petaflop computer specifically for civilian purposes. And what we're doing there, to give you an idea, is we're taking electrical models of the transmission system of an entire region, combining those with distribution models, so all the way down to the residential home level to solve very complex optimization problems and impact, looking at the impact of high penetration scenarios for PV and wind. Then if you go further down this corridor, we have 16 laboratories, and 5 of those are electrical, another set are thermal, and then fuel systems labs. And just to give you an idea, some of the research that's going on there, the Power Systems Integration Lab, we have, it's a megawatt scale testing capability, so AC and DC generation. That is connected to this smart power lab. I'll show how in a second, but this circle here too is a smart power lab where we have mock residential homes, and then an energy storage lab that's shown as 3. We also have an outdoor test area. It's a 480 volt test yard where we have microturbines, diesel generators, and load banks, and a 13.2 kV outdoor test yard for medium voltage systems, so for instance, large scale energy storage systems. So one of the unique aspects of this facility is that all of these different buildings that I mentioned, different program areas and research areas, are tied together through a research electrical distribution bus. So they're electrically connected through AC and DC buses and also through thermal buses. So we have natural gas that runs through. We also have hydrogen lines. We actually make our own hydrogen at the lab. And chilled water, and also SCADA. So this, by the way, I just wanted to emphasize that this was funded through taxpayer dollars. And this is now what's called a user facility, which means that DOE actually pays our O&M cost. So there's an operations room, and if you look here on the lower left, these boxes on this one-line diagram are the individual labs. So you can come in as a utility or as a company, if you wanted to do an ESI experiment, connect these laboratories together with other components and do an integrated experiment, and you would only pay for incremental research or cost. So this has been filling up rapidly with various industrial and utility customers. I won't go into detail on this other than mention that we, again, have megawatt testing capabilities here. I'll just show briefly one example. I showed the home and the ability to disconnect from the utility. We also do experiments here where we're taking electrical models that's shown in this tan block over to the right that says grid model. So if you would go in and model a grid and model a portion of a home, you can actually connect that model to real hardware. It's basically a co-simulation. And if you look down here on the bottom, the way that's done is that electrical model drives a grid simulator, which is connected to real hardware. So if I wanted, for instance, test a building component, or I wanted to test a controller in combination with hardware, I can combine that hardware with the model, and the way you do that is you take the electrical measurements that are happening in the experiment and tie it back to the grid simulator, and you can get a dynamic closed loop response at megawatt power levels. So it's a very powerful technique that's being used now at NREL. This is a CAD drawing, obviously, but this laboratory has been built with the exception of the PV that's actually on the roof. But there's an area for 3 homes. So we have, under various projects, we have appliances, complete kitchen appliances with washing machines, for instance, that can turn on not based on just hitting the button, but if you say, I want this done, but I don't care when it is, give me the signal that tells me it's the optimal time to use it and I'll turn on. That's that sort of technology. And the idea then, and what we're doing over the next year through DOE program funds, is to do integrated experiments where we take PV systems, for instance, in the Power Systems Integration Lab, connect to appliances in the Smart Power Lab, energy storage, electric vehicles outside, to do integrated experiments where we're vetting and developing that ESI or that LASIK model that I mentioned for ESI. And we're actually going beyond that in terms of creating a net zero energy campus. So if you look in the upper right here, this is the ESA facility, and this is actually a LEED Platinum building, despite the fact that we have a high-performance computer that burns about a megawatt continuously. And there are thermal loops that come out of that building, and which will be tied to the thermal loops on the campus. And I have a drawing here, or excuse me, a movie here. I'll show you so far what we've done is we have about 80,000 data points that are coming in continuously, about every second. And this is the energy flow. Let me put this on repeat. This is the energy flow on the campus. So it shows this is a typical campus here. This shows the greenhouse gas. And this is the NREL campus. So there's about 2 megawatts of solar on campus on this garage here and on the parking garage over here. And this building is completely covered with PV. This is the ESA facility up here. So what we're driving towards now is that controller, now rather than being applied in the ESA, it's applied throughout the entire campus. So why is this important? It's important because if you look at the goals that we have at a national level, which is to decarbonize our economy by 2050, then we have to decarbonize electricity first. So if we get to 80% clean energy by 2035, that means that we have to demonstrate systems at scale, meaning communities or residential systems like this by 2025. That's our goal. So to meet that, if you imagine that it takes about 5 years to deploy this technology, work out the bugs, you imagine that takes 5 years and work back. So we have about 5 to 6 years to do fundamental research to get this right in terms of the control architecture. So I'll continue here. So I just want to mention, I mentioned a specific facility, which is ESIF, but I want to talk about even higher level what's going on at DOE. There's actually been an unprecedented development recently where the different agencies within DOE, so EERE, Energy Efficiency and Renewable Energy, and Office of Electricity, have actually come together under one common goal, sharing the details of their programs and their funding for a topic called grid modernization. So leadership within DOE and the labs has identified several, 8 areas here, characteristics of a modern grid. And I won't read all these, but I'll point out a few. Resiliency, so harden the grid against attacks, either man-made or weather attacks. Adaptable and flexible, that's a favorite of mine. How do we design the grid to accommodate ceaseless change? And the one that's near and dear to our hearts, which is clean. So how do we make our electricity supply system dramatically cleaner? And there have also been a number of teams that have been set up. I have seven teams shown here. One of those I mentioned, cybersecurity. I'm on this team for security and emergency response. But again, the challenges are to improve and fix the aging infrastructure, fuel mix changes, et cetera, and the goals being, not only to maintain reliability and safety, but to increase security and resiliency. And then I also mentioned this 80% clean energy or clean electricity by 2035, with ESIF being one of the test beds to implement the ideas. So I'll leave you with the last 2 slides, which is some results from a study that's forthcoming, but this is on the Eastern Interconnect, and it gives a glimpse of what's needed in terms of a clean energy future. So if you look at, this is actually in the Southwest Power Pool, this shows current variable generation, wind. It's not much. It's hard to see, but I believe this is gigawatt scales here. So 23 gigawatts of wind. Then you have other capacity here, and in the lower left is the actual generation. And if you notice, the majority of the power generation here is coal. There's some nuclear, and on top of here, not much wind. Then if you look at, if you establish a renewable energy target of 30%, then we do studies to see what would happen. In this case, here is the variable generation capacity on the top right, and the bottom right is what would need to happen if you had as much wind as in these 2 or 3 days here in April. These are the windiest days that we have measurements for. What would happen is that you'd have so much wind and so much PV that you would need to ramp down coal nearly to 0. Well, if you do that, if you look at the red here on top of the curve, you would still, despite that, you would still have to curtail this energy. Now, once those assets are in place, this renewable energy through wind or solar is basically a free resource. So you want to avoid having to curtail that power. So the question is, how do you do that? And this is the topic of going beyond grid. So I showed the example of the home earlier. So if I take PV and combine that with energy storage, so I need a control methodology to determine, especially with solar forecasting, for instance, and load forecasting, how can I manage my energy more effectively? So that's inside the home. And right now, if you take a simple PV system that is operating 20% on load, then you could come up with about a 14 kilowatt per hour cost of PV. But we've done studies that show that if you take PV and combine that with energy storage, or actually smart controls, I should say, that it's possible to get down to 9 cents per kilowatt hour. And actually, there's a funding opportunity right now by DOE called SHINES that is specifically targeted towards coming up with new control technologies to get down to a levelized cost of energy of 14 cents per kilowatt hour or below. So that's on the demand side. But then on the supply side, there are opportunities here as well. So if, rather than curtailing wind and PV on my system, is it possible to take the thermal output of these plants and actually use them for other purposes, other industrial purposes, for instance, creating hydrogen or other chemicals that could be used for the industrial and transportation sector? So really what's needed, I mentioned energy systems integration, going beyond the components to an integrated solution, a scalable, flexible solution, but also looking at other opportunities within the energy system on the supply side and the demand side. And I'll leave it at that.